Chemical shift describes the location of a signal in an NMR spectrum. The variable that we use for chemical shift is the Greek letter delta, and the units are parts per million. The shift for a proton signal is calculated as a comparison to TMS, and TMS stands for tetramethylsilane, this compound right here. In order to calculate the chemical shift, we take the observed shift from tetramethylsilane in hertz and we divide that by the operating frequency of whatever instrument that we're using. So let's say, for example, I ran the NMR spectrum on benzene on a 300 megahertz instrument. Well, there's only one type of proton in benzene, so I'm only going to get one signal. I'll just draw the whole compound out here. So I'm only going to get one signal, again, because all of those protons are identical. But when I look at the chemical shift of benzene on a 300 megahertz instrument, what I see is that the observed shift for those protons from trimethylsilane, but when I run the NMR spectrum of benzene on a 300 megahertz instrument, what I see is that the shift of those protons from tetramethylsilane in hertz, when I divide that by the operating frequency of the instrument, which is 300 times 10 to the 6 hertz, I end up with this number, 7.27 times 10 to the negative 6. And we're going to see that number again when we use an instrument that operates at a different frequency. In many deuterated solvents, we add 1% tetramethylsilane, and that's added as an internal standard. And the reason why we use tetramethylsilane is because the frequency of the protons in tetramethylsilane are lower than that observed for most organic compounds that we would look at on a day-to-day basis. So we assign tetramethylsilane a chemical shift of 0 ppm. Again, the shift for a proton signal is calculated as a comparison to TMS. Now let's say I run an NMR spectrum on benzene on a 60 megahertz instrument. Well, what you're going to see is that the observed shift of those protons in benzene from tetramethylsilane is actually different than what it was in the 300 megahertz instrument. But when we calculate the chemical shift, we take the observed shift and we divide it by the operating frequency of the instrument. And what's interesting is that my chemical shift ends up being the same number that it was when I used the 300 megahertz instrument. The reason this is important is because the frequency of the signal is different in different instruments, but the shift, or the chemical shift relative to TMS, is going to be constant. So if my chemical shift is 7.27 times 10 to the negative 6 on a 60 or a 300 megahertz instrument, it's going to be that number on a 500 megahertz or a 600 megahertz or an 800 megahertz instrument. And the reason that's important is because organic chemists all over the world have to be able to collaborate with each other, even though they might be using NMR spectrometers with different operating frequencies. Now, going back to the formula for calculating chemical shift, you see that chemical shift is actually a dimensionless number because the units of hertz cancel out. So the units for chemical shift are usually reported as parts per million, or ppm, which really just indicates that the signals are reported as a fraction of the operating frequency of the spectrometer. Most of the signals that you see in a proton NMR spectrum appear between 0 and 12 parts per million. In rare cases, it is possible to observe a signal occurring at a chemical shift below 0 parts per million, which results from a proton that absorbs a lower frequency than TMS. But this is very rare. Modern NMR spectrometers maintain a constant magnetic field strength and pulse the sample with all relevant frequencies of electromagnetic radiation. But early NMRs operated a little bit differently. And these early NMR spectrometers were called continuous wave spectrometers because they would hold the frequency of radiation constant and slowly increase the magnetic field strength while monitoring which field strengths produced a signal. Signals on the left side of the spectrum were produced at lower field strength, and we call that downfield, while signals on the right side of the spectrum were produced at a higher magnetic field strength, and we call that upfield. And if you think about it, shielded protons are going to require a stronger magnetic field to be excited at the same energy as deshielded protons. And what I mean by energy is the electromagnetic radiation, which was held constant in these old continuous wave spectrometers. Despite the advent of the modern Fourier transform spectrometer, the old terms downfield and upfield are still commonly used to describe the position of a signal in an NMR spectrum. So so I will refer to upfield and downfield throughout these videos. So current NMRs analyze samples at a constant field strength over a range of energies of electromagnetic radiation. Now protons that are shielded by having more electrons around them have a smaller magnetic force acting on them. So they're going to have a smaller energy gap between the alpha and the beta spin states, and they're going to absorb lower energy radio waves. And that is why shielded protons are upfield. The opposite holds true for deshielded protons, which will absorb higher energy radio waves and will be shifted downfield. Alkane protons generally give signals around 1 to 2 parts per million. So whether it's methane, ethane, propane, butane, so on and so forth, the protons will usually be around 1 to 2 parts per million. The protons in an alkane can be shifted downfield when the nearby electronegative atoms cause deshielding. So what you see right here is that methane has a chemical shift of 1.0 parts per million. Again, all 4 protons are identical. But what happens when I add a halogen like iodine to the molecule? You can see that the chemical shift increases by 1.2 parts per million to give me a chemical shift of 2.2 parts per million for iodomethane. And you can see that that effect is exacerbated as I add more and more electronegative elements until I get up to fluoromethane, which has a chemical shift of 4.3 parts per million. So what's happening in each one of these methyl halides is that the electronegative element is withdrawing electron density away from those hydrogen atoms. Therefore, they are being deshielded, which causes them to have a higher chemical shift. Looking at these 3 examples here, you can see that the effect of adding a halogen is additive. If I go from chloromethane to dichloromethane to chloroform, I get an increase in chemical shift as I add more chlorines to the molecule. And this is due to the increased electron withdrawing effects of having more halogens added to my molecule. So the overall effect of these halogens is deshielding, and deshielding results in a higher chemical shift. And what you can see in the blue box is that each chlorine atom adds approximately 2 parts per million to the chemical shift of the signal. You can see that the inductive effect tapers off drastically with distance, as can be seen by comparing the chemical shifts of the protons in 1-chloropropane in the yellow box. So the protons that are alpha to the chlorine are the most deshielded, and therefore they have the highest chemical shift. You can see the effect tapers off on the beta carbon, which has an increased chemical shift compared to the 3 protons out here in the methyl group. The reason that the effect is less pronounced is because it's farther away from the chlorine atom. Once I get to the gamma carbon, there's virtually no effect at all from the chlorine.